Okay, so here's an example from class 22. And this is one very similar to one that was done in classes, I believe, 6 and 8. But this time for rigid body motion, the pulleys in the previous ones were massless. Now the pulley, you could think of the pulley as having a large mass. So we want to try to compare these 4 different scenarios. We have 160 pound of force being applied to this pulley with a large mass. And we have 160 pounds weight that's on the end. And then we have a differential of 460 and 300. So there's a differential of 160 pounds between these two masses. And then we have one over here where I believe I guess it's just an 80 pounds. All right. So I think the outside radius. Okay, so what happens? Okay, I'm sorry. So there's 80 pounds, but this is going to be on the outside of this pulley as opposed to the inner pulley on this one right here. So, and there's like 9 inches and 18 inches. So what happens right here is we essentially have the same scenario in 4 as we do in 2, except that now the weight is less, but the position of it is further outwards, right? So if you were to think about that weight times that moment arm, they would essentially be the same thing, right? 160 times 9 is going to be equal to 80 times 18, although don't ask me what the answer on the top of my head is. So let's take a look at the first scenario right here. Okay, we're using work energy as part of this. So that force that we're applying is going to move down 10 feet, right? Something that we're going to need to know for all of the first 3 scenarios is this velocity that we would find at A is going to be related to the angular velocity by that 9/12 or 0.75 omega. So in this scenario here, we start off with the thing at rest. So kinetic energy is 0. We're going to start as a datum. We'll keep the datum. Well, actually, there's no change. So the potential energy is 0 in this case, and will remain 0 because there's nothing changing spot. So the energy that's added to this is that 160 pounds through 10 feet, right? And those are in line with each other, so and in the same direction, so they're positive. So 1,600 foot-pounds. And then the kinetic energy when we're done is entirely going to be rotational kinetic energy, or 1/2 I omega squared. And we were given the moment of inertia of 16 as part of this. I think the units were something weird, but they're actually the units. Let's see, I'll look up on the sheet here without going back to the thing. Yeah, they gave units of pound, feet, second squared. Those are the same things as a foot second squared, just a slug foot squared. So the pound foot second squared is the same thing as a slug foot squared. Confusing. So we have 8 omega. The potential energy doesn't change. And so we set it up into our main equation here and plug these in. And so all we have is this external work that's creating kinetic energy. And we're able to find what the what the angular velocity is when you're done. So in the second scenario, instead of having a force pulling down, we have a weight or a mass of the same value, but now what we're going to find is it too is going to contribute, and it's going to have a potential energy. It begins with a potential energy of 1,600 foot-pounds, right? Which is essentially the same thing as this this external work, right? That's over here on the left-hand side. But in this case, it's a conservation of energy, so there is no external work. But the kinetic energy has 2 parts. One is that rotational kinetic energy. The other is the translational kinetic energy, right? By the way, this is not a scenario where the parallel axis theorem applies, because this is not, these are 2 different particles right in here. We're not trying to find the composite, if you will, of this. And what we find now is that we're going to have 9.398 omega squared. And the potential energy is 0 at the end. So we plug these guys in, and we end up finding that it actually goes slower than it would if there was 160 pounds of force applied to the thing. Now 160 pounds, that's part of a weight that has mass, it tends to make the thing more sluggish, right? Because now that too has to gain kinetic energy. Now in the third scenario here, we have pretty much all the same things, except now we have a differential of 160 pounds. But as you can imagine, if you think about what happened between the first incident and the first scenario and the second scenario, now you can imagine the third scenario, it's going to go even slower because there's even more mass that needs to come up. There is going to be a difference in potential energy, so we want to take account of that. Let's only look. So we'll, in essence, draw two datums, right? One of the datums is going to be right here, right? And then the other datum is going to be right here, right? So the datum for C is right at the first instant, it's going to make it 0. And the datum for B means that it has a potential energy of that 460 times 10. No external energy. And the kinetic energy, I accidentally left off that it should be plus 1/2 mc vc squared right in here. I kept it in right there, and you can see that we're still using that 0.75. That they're on the same pulley right there, so that's not a big concern. And so we end up seeing that we have 14.64. Now we do have a potential energy in the second, because this thing has lifted from the datum to its new location. And we plug these into our setup here, and we find, sure enough, it does have a slower angular velocity after the weight has moved 10 feet. And then our last scenario right here, we are actually on the outside of the pulley with a lesser weight. So this is really more comparable to scenario 2. And by the way, also the velocity has a different relationship with omega because it's on the further out on the radius. So we take the initial kinetic energy, starts from 0. Our potential energy is only going to be from here to here, right? So it's only going to change 80 pounds through 10 feet, so 800 foot-pounds. And then the kinetic energy is still going to be the combination of, just like it was over here, of the rotational and translational kinetic energies. And we get 10.80 omega squared. And then, which is a little surprising to me. No, okay, because the 1.5 ends up being squared, that's why. And so we plug these in, and we find we get even less, 8.609 feet per second. So it's interesting because all of these you could make, if you just jump to the conclusion from looking at that without actually working through the problem, you might conclude that these were all going to be the same. This is the type of problem that would get asked in a multiple choice question on, say, like the FE exam. They might only ask about like which one is going to be more, or which one's going to be less, or they might ask something along those lines, and then you could have a whole bunch of different choices as the answers. But it's a good dynamics thought problem. So that's going to be example 1 for here. We can discard all that stuff. For our guitar of the day, because we're running out of time, and I'm not running out of guitars, we have one that I made of parts, right? So this is from Warmouth. I like Warmouth a lot, so he's got no name on it right there. That's kind of cool. It's actually a bolt-on. Most guitars that you would see like this would be like Gibson types of guitars that would be neck through body. But somebody was selling these parts like really cheap, and so I bought the bridge and the pickups. I can't remember where I got them from. I just borrowed them off some other guitar. I have a big box of pickups. So I like to change them out. There's nothing exciting about this guitar. It's just a good all-around useful guitar. So one of my best friends from college, he got divorced, and his wife, when she kicked him out of the house, she got a lawyer right away, and he's got a larger guitar collection than I do, and some of them are quite expensive. So anyway, for the next year and a half or during the divorce, they wouldn't release any guitars to him. So he was like singing the blues, and so I sent him this guitar. So he owned this guitar. He had this guitar for about like 5 years. But when he finally got his guitars back, he gave me this one back. Moral of the story, kids, don't get divorced.